Hi and welcome. In previous video we have seen about the direct addressing. In this we will be beginning with open addressing and seeing the first one, that is linear probing. So what is open addressing? So suppose we have our hash table, okay, and we have a collision. Fine. So here two elements are colliding at this slot index. So what happens in open addressing is there is no linked list created. Everything is stored inside the hash table itself. First point. Second point is that once there is a collision, so a new slot for the collided element, there will be a new slot index that will be calculated using the same hash function with some minor modifications. We will see what are those. So if x is present here and another element come to the same index, so what happens is either it will be stored in the next one, or we will see what there are other possibilities, but the first one in linear probing we will see it will be stored in the next one. So whenever there is a collision, a new slot index is being calculated using the same hash function. So in open addressing, all the keys are stored in the hash table itself. Okay, this is also known as the closed hashing, inside the hash table only. Now because all the keys are inside the hash table, so the maximum number of keys are directly proportional to the size of the table. So if the size of the table is 10, we can store only 10 keys. If it is 11, we can store only 11 keys. But as you remember, in the direct addressing, if the size of the table is 10, we can store 100 keys also. Okay, so there this was possible, but here it is not possible. So the load factor is always between 0 to 1. Why? Because now let's see, there are n by s is the load factor, number of elements, number of keys upon the size of the hash table. Now these two are same, okay, the maximum is same, so it is nothing but 1, and the minimum is 0. Fine. If let's say it is 10 and we have 5 elements, so it is nothing but 0.5. so the alpha, that is nothing but the load factor, will be always present between 0 to 1, because in this there is a restriction that the number of keys maximum can be equal to the number of size, the size of the hash table itself. Okay, so that is the second point. And third point, now if there is a collision, then with minor modifications in a hash function, a different slot index is calculated. Now what is probing? Probing is finding the slot index that we are doing. Okay, we are doing probing only, is finding nothing but the slot index. So in open addressing we have to probe many number of times. Okay, so if there is a collision, we will probe again. Then if there is a collision there also, we will probe again. Then if there is a collision in the next index also, we will probe again. Okay, so we are going to probe till we find a suitable index to store that particular key. Okay, and if it is not possible to store that particular key, we will simply return false. Fine, or we will print it is not possible. So this was the introduction to open addressing. Okay, why is the load factor between 0 to 1 and what are the modifications? Let's see now the linear probing, that is the first type of open addressing. Okay, now in linear probing what happens is, let's suppose we have this hash table. Okay, now in this 0 to 0, 1, 2, 3, 4, 5, 6, 6, so its length is nothing but 7. So we cannot have more than 7 keys inserted into the hash table. If we have more than 7 keys, then when all the slots are completely full, then it will just simply tell hash table is full. Okay, so let's suppose we need to insert 23, 33, 25, 45. Okay, and with the hash function of mod 6 this time. Fine, so 23 mod 6 will give me the value of 5, and let's say this 35, so 35 mod 6 will give me a value of 5. Okay, so 23, 6 is 24, and yes, it will be 5. So now both are, first it will be mapped to 5, so yes, 23 will be inserted. Fine, now the second one comes. When the second one comes, that is 35, and it is also mapped to 5, what happens in the linear probing? In the linear probing is that the hash function needs to calculate a different slot index. Okay, now what is that different slot index? So it is nothing but the next slot. It is nothing but the next slot. It linearly increases the slots. Okay, so if my h of k, that is h of key, gives me a particular slot index, okay, and there is a collision, so again a hash function is calculated. Okay, again a hash function is calculated with my h of key, whatever was there, okay, plus I. What is this plus I? This plus I is nothing but the number of times we have actually, the number of times this collision has happened till now. So this the new hash function will be nothing but, okay, let me just make a correction. It is nothing but, the new one will be nothing but hash of key plus I, which is simply the first one, hash of key, that we have already calculated, plus I mod f, the hash function, or mod the max size of the this one hash table that we are creating. This is the hash function we are using, always mod with the max size. So this is how it will work. Now let's say we have done and the I value is 1, that means there is the first collision. So how it will work, hash of key comma 1 is nothing but the slot index that was calculated plus 1 mod max. Then it will be slot index that was calculated plus 2 mod max. Then it will be nothing but slot index calculated plus 3. So if there are 2 collisions, then we are coming here, so mod max. Now if there are 3 collisions, then slot index plus 4. Okay, so every time the original slot index that was calculated is increasing by 1. It is that simple. Okay, it is so simple. So every time the slot index is nothing but increases by 1. So if this is my hash table and here there is a collision, in the first prop the slot index was this. In the next prop the slot index will be this. If there is a collision here also, then in the next slot this will be the prop index. Then in the next one this will be the slot index. When if we find a cell that is empty, we will be inserting the key here. If we do not and we are at the last, we will simply move to the first one again and we will cycle back. Okay, now while cycling back, if we reach to the first slot itself, then we are going to say that all the elements are full, all the indexes are full and there is no space, so the hash is full, hash table is full. Okay, so one by one we will be simply, if this is a collision, then check for this, if this is a collision, check for this, if this is a collision, check here, and one by one linearly we will be increasing. Fine. So this is what linear probing is. It's that simple. So each and every time the original slot will be added a new value, and that will be nothing but the previous value plus 1. Fine. So in linear probing we search the hash table sequentially. Okay, starting from the original hash location. So originally hash location was calculated as slot, then plus 1, plus 2, plus 3, so on. If a location is occupied, we check for the next location and we wrap around the last table location to the first table location if it is necessary. Okay, now what is the problem in this particular, what is the disadvantage here? So let's see. Now if we have a hash table, okay, now we have a hash table, okay, and suppose we have 24 or 23, so this is 3, correct? Now again something comes like 43 and again it is mapped to 3. So what will happen, it will check for the next one. Now we have 53, again it is mapped to 3, so it will check for the next one. Now it will be here, then comes 63, then it will come here. From the beginning it will begin here, check this, check this, check this, then it will be inserted. Then 73, it will begin with this 3, check, 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 and then insert. Okay, same for 83, begin with this, check, 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 and then insert. So what is happening here is, if an element is mapped to a particular slot, okay, and if another element is also mapped to a particular slot, then they will follow the exact prop sequence. They will follow the exact same prop sequence. So 73 is also following the exact same prop sequence as 43, 53, 63 before it is inserted. Okay, if the slot is empty. Fine. Also there is something known as clustering here. So because all these are mapped to the same slot sequence, okay, and the first slot that is empty, we are actually inserting that. So there is a clustering in a particular size of the array, in a particular part of the hash table. Okay, so this is more dense, and here we have no elements, and here we have no elements. So the problem here is nothing but of clustering. So let me just read it out. One of the problems with linear probing is that the table items tend to cluster together in the hash table. This means that table contains groups of consecutively occupied locations, that is called clustering. Why? Because see, we have elements and all of them are actually starting with the same position. So all are following the same pattern. All are following the same pattern. And the next location that is free, they are inserting there. So it is not that 63 starting from here, it is free and it is inserted. No, it will be following the same pattern. Okay. Clusters can get close to one another and merge into a large cluster. Thus, one part of the table is quite dense, even though the another part is relatively has few items. So cluster causes long prop searches and therefore decreases the overall efficiency. Now how it decreases the overall efficiency? Now let's see. If we are going to insert, so isn't it in the worst case it will be order of the size of the hash table? Fine, because if I just increase 93, 103, and now 113 needs to be inserted at this position. It will begin with this 3 and it will roll back again to the last position, to the third position here. So 113 needs to be inserted, have to be checked for each and every slot, so therefore order of size. Now similarly for searching, in the worst case it can go till order of size, but definitely we will be not using such a hash function that does this. It will have even distributions. Therefore what happens in the average case is, I'm not going to go into the probability, it is nothing but 0.25, okay, around. So this is nothing but constant, so this is calculated using mathematics, so that we are not going to go into that. But this was the average, this is the average experiment case, okay, the time complexity. In the worst case, yes, it is order of s, that is nothing but the size of the hash table that we are having. So this is the problem with the linear probing, that clusters form and nothing else. But it is quite simple to implement linear probing. As you can see, we have to just increment the index by 1 for the next one. So this is quite simple to implement, okay, and practically it is of constant time searching, so it is widely used. Okay, fine. So let's see the implementation of linear probing, and after that we are going to go into the next video with quadratic probing. Okay, let's see the implementation now. Let's begin with the implementation now. So before seeing the main function, let's see the class of hash slots. So what it will have is nothing but what the slot will look like. So a slot will have a key and a value inside of it, correct? So a constructor to declare to initialize those values. So this one slot will look like something like this one slot, okay? So after this we are going to create an array that will contain these slots. So each and every of these slot has a key and a value inside of it. Fine. So this is that array created, okay? Now this is nothing but table size, what is the maximum capacity we want, and the size will have, whenever we insert an element, the size will be increasing, okay? Using a constructor, we are going to initialize everything, our array, table size, and the size. So in the beginning table, all the array, that is nothing but our hash table, each and every slot will be null, okay, nothing inside of it. A get size function, a clear function that we have already seen before also. Now how our insertion is happening inside of this? First, obviously what we are doing, we are using our hash function and we are getting our index. So if it is 45 and hash is nothing but 10, so 45 more 10 is 5, so this is nothing but the slot index. We will go to the slot index 5, okay. Now if it is null, we are going to simply create insert create a slot and insert the value inside this particular index and increment the size. Now if the key is already present, so what we are going to do, we are going to say duplicate keys are not allowed, and if nothing is the case, then we are going to linear probe it. So that means value is already present inside of it, so we do linear probe and check for the next element. If the value is already present, then check for the next element till we get an element that is null right now. That means table I is null. Till we get this, we are going to linearly probe it. So when we are going to stop it, we are going to stop it when it comes back, correct, to at this position again. When I is not equal to index, so it will loop. When I equal to index, it will stop, okay, and it will stop, so it will print that hash table is full. If we are going to insert, we are going to return from that particular line only. Fine. So this is the insert function. And what is the search function here? So here in the search function, how we are searching is nothing but we are traversing the array. If table I is null, return false. At that particular index, if it is nothing, return false. If the key is found, return true, or linearly probe it. As simple as that. And the same do while loop. If whole do while loop is over and we do not find the key, then also return false. A simple search element function. Display function also same. So what we are doing in display function is nothing but for order table, we are nothing but traversing our table. If it is null, hash table has no element. If it is not null, then key and value present at that particular index is printed. As simple as that. Now for the main function, what we are doing, we are getting the input that what is the maximum size of the hash table. We are creating the hash table of that particular size. We are inserting just 6 elements into our hash table, getting key value and insert. Then we are displaying it. We are searching for a key 25, it is present, and key 25 is present, else key 25 is not present. Then we are getting the size of our hash table. We will clear it and then we will print the size again. Fine. So let's just run this particular code now. So these are the 6 values that we have, and we just need to get the maximum size first. So let the size be 10. Then we have 6 values, and here are the elements. So first 25 will come. 25 will be at hash table 5. Okay. then 36 will come at the hash table 6. They both were null in the beginning, so they will be directly inserted. 125 will come. It will begin with 5, but it is not null. It will get 6, but it is not null, so it will go to 7. It is null and it will be stored. For 457, so it will begin with 7, but it is not null, so it will go to 8 and it will be stored. 11 will be at 1, 69 will be at 9, 25 is present inside the table, so it is present. Size is 6, and when we clear it, the size is 0. So this was our simple linear probing function. Fine. So this was the internal working of the linear probing. While competitive programming or like coding, we will directly use the hash map given to us by the inbuilt functions in the collection framework. Okay. Thank you.